So here comes the omnipresent Ethernet technology. I will cover only the technology details in this video. The actual MAC CSMA CD will be covered as part of another video. Ethernet is a very successful and widely used technology. As of 2010, it has a market of about $16 billion per year. It's also very cheap. A 100 Mbps network adapter costs about $5, roughly 300 rupees. When Ethernet was originally standardized, it provided a speed of about 10 Mbps. Now we have 100 Gbps Ethernet. That is a 10,000 times increase in speed in a matter of about 30 years. That's incredible. Ethernet works over different speeds, as I have mentioned above, as well as different physical media, coaxial cable, twisted pair, fiber optics, and so on. So there are different working groups that cater to the different standards. All of them fall under this umbrella of IEEE 802.3. So why do we have standards? Basically, they ensure that the equipment manufactured by the different vendors is interoperable. If you don't have a standard, then they won't work together. So let's see how Ethernet evolved over the years. In 1970s, Metcalfe conceived the idea of Ethernet. Here is his Ethernet sketch. Basically, it was a bus topology. So up to early 90s, this bus topology was very popular. This was based on coaxial cable, and here is a picture of how the equipment looked. And there were two types. One was called thicknet and another was thinnet. Here is the standard corresponding to thicknet. What do these numbers mean? 10 refers to the Mbps, so this offered 10 Mbps. Base refers to baseband modulation. Remember, I've told you earlier about baseband and passband modulation. So what encoding technique does 10 Mbps Ethernet employ? Right, Manchester. And the number 5 here refers to the fact that this Ethernet can work over 500 meters. There is a restriction on distance. Why such a restriction? I will cover later. Similarly, thinnet, again, here 10 refers to 10 Mbps base, means baseband modulation. 2 refers to the fact that this cable can only be used up to 200 meters. Since many nodes share the bus topology, there is a need for media access control, and Ethernet employs a media access control called CSMA CD. As I mentioned, I will cover this in detail in another video. So this bus topology had a good run for some time, but then there were many problems associated with it. For one, these coaxial cables were quite expensive. And not only that, when you have a bus topology with many nodes connected to it, and if there is a fault or break in the cable, it affects all the nodes. Not only that, for you to add or remove nodes, you have to disrupt the entire network. So people decided bus is not the way to go, and the cabling issues led to a star topology. So in star topology, the hosts were connected through what is called a hub or a switch. I'll get to this shortly. And various standards emerged catering to this. 10 base T refers to the fact that it is 10 Mbps Ethernet operating over twisted pair. T stands for twisted pair. This is 100 base T, which is 100 Mbps Ethernet operating over twisted pair. This is also called fast Ethernet. And then there was gigabit Ethernet providing 1 Gbps, again operating over twisted pair. So this move to twisted pair reduced the cost of Ethernet significantly because most buildings already had twisted pairs installed in them. Why? Because this is the same link that is used as part of telephone network. So now you have very low cost technology. Not only that, the star topology made network management as well as debugging the networks very easy. For example, if there was a fault here, this wouldn't disrupt the other nodes. And also it is easy to identify where the fault is as part of the hub design. So star topology of course had a fundamental flaw. What is this? We covered before. Basically that if the hub or switch failed, then of course the whole network failed. But this equipment was designed carefully to be more reliable. So their failures were rather rare. Now what is this hub or a switch? Hub is nothing but a physical layer repeater. All it does is it takes bits from one link and puts it out on all link at the same rate after boosting up the energy. This boosting is done so that the signal can travel over longer distances. A hub does no frame buffering. It does not even implement a MAC protocol. So using a hub, you could interconnect the different hosts in this particular fashion. One thing to note here is you cannot connect a 10 base T hub with a 100 base T hub. They have to have the same speed. One important point to note here is that this is one big collision domain. In other words, if this host were to send a packet, this packet goes to each and every host as part of this network. So if two hosts were to simultaneously send a packet, it is going to result in a collision. That is why you need a media access control as part of this particular topology. So a hub can increase the distance, but this is not a whole lot. There are many restrictions in the use of hubs as well as the length of the cables. For example, in 10 base T, a host, the computer to a hub distance should be under 100 meters. And you can have at most 4 such repeaters or hubs leading to an overall network diameter of only 500 meters. In 10 base 5, which is coaxial cable based, you can have a distance of up to 500 meters between the terminal, the computer and the hub, and you can have at most 4 repeaters leading to a diameter of about 2.5 kilometers. By network diameter, I basically mean the distance between, maximum distance between two hosts that are within the same collision domain. In 100 base T, where the speed has increased to 100 Mbps, again the terminal to hub distance, because you're using twisted pair, is 100 meters. This is wrong. This is 100 meters. And you could use only at most 2 repeaters. And in this case, the diameter has reduced to just 200 meters. Why these restrictions in terms of distance? This has got more to do with the MAC protocol rather than attenuation, as this will become clear when I cover the CSMA-CD MAC protocol. Not only that, the maximum number of hosts that can be part of one single collision domain is again restricted to 1024. Again, this has to do with the MAC protocol. But this you can guess as to why. Why do you think we want to limit the number of hosts within a collision domain? That is right. As the number of hosts increase, the probability of collision increases, and thereby your throughput is going to fall. That's with respect to hub. Switches are very different from hubs. There are also called Ethernet bridges. The switch configuration is the most used configuration. These days you don't even see hubs. All machines are connected through switches. What does a switch do? Basically, it transfers frames from an input to an output link. Well, this is what a hub did, but a switch can buffer packets. Not only that, a switch runs a MAC protocol on each interface. For example, if you look at this equipment, this has 48 ports. By ports, I mean it can support 48 hosts, and on each of that interface connecting to a host, it will run a MAC protocol, which is the CSMA-CD. One big advantage of switches is that they can help break up the collision domain. I will show an example shortly. Switches can switch speeds also. For example, if this is being connected through a 10 Mbps link, you can potentially switch the speed to 100 Mbps. This is possible because it buffers the packet and then again transmits the packet on this other link using the media access control protocol corresponding to that link. So here is interconnection with the switch. Notice that there are 3 hubs which are connected to a switch, and remember that a switch on each of these interfaces, it is going to run a media access control, and it isolates these. Given that, how many collision domains does this particular topology have? That's right, 3 separate collision domains. For example, if this host has a packet to send to some other host here, all it has to worry about is to send the packet to that particular switch. So it is going to compete with the switch and as well as this other host to transmit the packet. Once this packet reaches the switch is going to buffer the packet, and then it is going to again contend with all these other hosts as part of this collision domain, and going to send the packet to the designated destination. Just to emphasize, this collision domain has 4 stations, 1, 2, 3, as well as the switch competing for access to the media. Once this packet reaches the switch is going to compete again with these 3 other hosts to access this media to deliver it to the right destination. So use of switches can significantly increase the reach of the network. For example, if you were employing the 10 base T, as I said, there is a restriction of only 500 meters here. But if you interconnect it through a switch, you can potentially span few kilometers. So a question should have popped in your head as to how does the switch route packets. We will cover all this as part of Ethernet switching in another video. When you employ switches, there are 2 modes of operation. One is the shared mode, which is also called half duplex mode, and in this mode you employ the media access control protocol CSMACD. So this is an example where the switch is operating in a half duplex mode. A switch can also operate in a full duplex mode. In full duplex mode, each station is connected to the switch using 2 pairs of wires, one for transmitting and one for receiving. Basically, this link is going to be a full duplex link. Given this, do you see there is a need for media access control here? That's right, there is really no need for media access control because this is like a point-to-point link and there is no one competing against this particular link. By the way, the same topology could also be supported in half duplex mode where this link is a half duplex link, and there is going to be contention there because to access this link you have the switch as well as the station trying to compete, and you have to resolve contention between the switch and the host. Whereas in a full duplex link there are 2 pairs, thereby there is no contention. Ethernet as such provides what is called a connectionless service. By connectionless, I mean that the sender and receiver do not do any handshake before transmitting the packet. So the sender, whether the receiver is alive or not, will just send a packet. It doesn't care about the status of the receiver. Whereas if you typically employ handshaking like in TCP, you ascertain the status of the receiver before you send packets. But Ethernet as such is a connectionless service. Not only that, it is an unreliable service. In other words, it does not provide any means for recovering lost frames. If a packet is lost due to errors, it does not implement any reliability. If you want reliability, you need to employ TCP at the higher layer. Just to clarify a point here, I mentioned earlier that random access protocols, whenever they see a collision, do retry later to retransmit the packet. That is not the same as providing reliability. If your media access control protocol didn't even recover from collisions, it wouldn't be much of a media access control protocol. So you do need to recover from collisions, but you don't have to recover from errors resulting from high noise or crosstalk or interference. So here is the Ethernet frame structure. It has this combination of preamble and SFD. It can be viewed as a sentinel, which we covered as part of framing. The preamble is nothing but a sequence of alternating ones and zeros, mainly used for synchronization. The SFD is also a series of ones and zeros, except that it ends with 1 1 just to show that this preamble has ended and the header has started. Following the preamble is the destination address and the source address. These are 48-bit long. This is also called the MAC address, often expressed in hexadecimal like this. If you want to know what the MAC address of your Ethernet adapter is, if you type ifconfig eth0, you will see this is in Linux. If you're in Windows, if you do ipconfig, you can figure out what the MAC address of your Ethernet adapter is. The type field is a demultiplexing key. Basically, it specifies which higher layer protocol this packet has to pass to, IP or ICMP or so on and so forth. After the type field is the IP payload. Again, this can take values between 46 bytes up to 1500 bytes. Notice that there is a minimum size requirement. Why? Again, we will cover as part of the MAC protocol. And after the data is the CRC, which does error detection. Another thing to note is you have to maintain a gap of 96 bits or 12 bytes between two frames. This is basically to ensure that the receiver has enough time to process this packet before it can receive the next frame, like empty the buffer and so on. So let's quickly also look at the Ethernet addresses. Each adapter has a unique address. Note that I'm not using host. A host can have multiple adapters. Each network adapter has a unique address, and this uniqueness is basically ensured by giving each manufacturer a different prefix. So for example, if Intel is manufacturing these adapters, this is the prefix that it will use. In normal mode, whenever an adapter receives a frame, it passes up the frame if the frame is addressed to it. This is the unicast mode. In other words, it will see whether the destination address in the frame matches its own address. If so, it passes up the frame. It will also accept the frame if the address is broadcast address. Broadcast address is nothing but all ones. This in hexadecimal will turn out to be all FFs. It will also accept a frame with a multicast address if it belongs to the group. In multicast address, the first bit is always 1. And you have to configure your adapter to accept frames corresponding to this multicast address. So that's more or less what is to know about the Ethernet technology. In summary, Ethernet underwent significant evolution over the years. It started out with 10 Mbps. Now we are dealing with 100 Gbps Ethernet. The speed increased by 10,000 times. Ethernet operates over a variety of media. I mentioned coaxial and twisted pair. It can also work over fiber optics. It went from bus topology to star topology. Within the star topology, originally hubs were used, but with the use of switches, this even circumvented the need for a media access control. So these days, there is no media access control used as part of Ethernet. So there are many standards that cater to the various versions of Ethernet. For example, 802.3i is the 10 base T standard, 802.3u is the fast Ethernet standard, 802.3ab is the gigabit Ethernet standard, 802.3x is the full duplex standard. If you look up in Wikipedia about the number of standards 802.3 family has, you'll be amazed by the range. The only thing that has remained constant in the evolution of Ethernet is the frame format. Going forward, we will look at the media access control employed by Ethernet, basically CSMA/CD. This is applicable only in the shared mode, that is the half duplex mode. This is not applicable in the full duplex mode.